In this video, we're working through some characteristics of graphs. We call this one level 1. We'll do some more later on. Our objectives include interval and set builder notation, continuous functions and domain restrictions, and then we'll determine where a function's discontinuous from the graph and look at limits a little bit. So we start with interval and set builder notation, and a recall. When working with equations, the domain is often thought of as a set of all valid inputs, or what we looked at before, the x values. And the range is a set of all outputs, so we call those the y values or function values. Note here, with the functions we work with throughout the course and in the calculus, we won't generally be able to list every value in the domain or range. Instead, we'll utilize interval or set builder notation to list the sets of values. So you may remember in one of the first videos we had a collection of points and we were looking at the mappings and we could pick out every single x and y. In general, we won't be able to do that. You already saw lines, and we have the collection of all points that satisfy the equation, create the graph of the line. There's infinitely many points that do that, so we'll have infinitely many values in our domains and ranges for many functions. So we'll look through this interval notation. Set builder is kind of follows right from the words. So to indicate all values or all numbers between a and b, we've got an open parenthesis with an a, comma, b with a parenthesis. So just between a and b, we don't include a and b themselves. We'll talk about how to do that below if you haven't seen it in a while. And for the set builder notation, one thing to point out, this little bar here is read as such that. So we can say it's all x such that x is between a and b. All right, all numbers greater than a. We start at a and go bigger, so off to positive infinity on that number line. And set notation, we have that x such that x is greater than a. All numbers less than b. So if we're going less than b, we're starting all the way at the left end of the number line, negative infinity, coming up to b and stopping. And in our set notation, x such that x is less than b. For all numbers less than a or greater than b, we've got two pieces. So from negative infinity up to a, and then we use this big cup or big U for a union to also include the values from b off to infinity, so greater than b. In set builder, we can say x such that x is less than a or x is greater than b. And if you've done like compound inequalities before, maybe we'll get to that at some point in this class, but the or is the big cup. So we're taking these two things together. And for all real numbers, we'll do the whole number line, so minus infinity to infinity. And we can read the set builder, x such that x is a real number. You can also, if you like some symbols, x belongs to this double R is the set of real numbers. And note here, to include the endpoints of the intervals, we replace the parentheses with a square bracket. So if we wanted greater than or equal to a, we could do bracket a to infinity. And we'll look at that when we write out some domains and ranges throughout this lesson. So for one here, we want to determine whether the following graphs represent functions, and then find the domain and range of each. So if we remember back to earlier sections, we need to check this vertical line test to see if we are a function or not. You can hopefully see any vertical line for the first one would only intersect once. So this is a function. We can say again that it passes that vertical line test. You can draw some on there if you want to see it. Domain-wise, you might recognize this as that exponential function from our toolkit functions. It's going to run out along that x-axis forever and then go up and out towards infinity. So domain is all of the x values. Let's use green for domain. We can use red for range for a little alliteration. So it's going to run everywhere left and right. So our domain here is going to be all real numbers, or for every x we input, we get an output value. For the range, we're looking up and down the graph. So it doesn't ever hit that x-axis. So we can think like an open circle there. We don't quite get there, but it will extend up, up, up forever. So we'll have every y value represented by this function above the x-axis. So we can use a parenthesis for the 0 since we can't ever hit 0, but then we go off towards positive infinity, so we can hit all those values. For b, we can find multiple lines that intersect more than once here, so not a function. right? This one fails that vertical line test. We don't care if there's some that would only intersect once or none at all, but as long as there's one that intersects more than once, it is not a function. For domain, we're looking at the input or x values represented by the graph, or those values that have an input, or when input to the equation, give us a value. And in this case, we can see, again, that vertical line thing. For most of the x values we sub in, they'd lead to 2 different y values on the graph. But every value between -2 and 2 gives us a point on the circle. For the range, we're looking up and down again. So we can see this point, or this range, these values start from -2 at the bottom and extend up to 2. We can see every y value represented somewhere on the graph. For C, we've got a function. This one again passes the vertical line test. You can see it extends up and to the right, down and to the left forever. So if we're thinking domain values, very clearly from like -2 to 2 on here, but then it also goes forever out to the right as that graph keeps extending up and right, and forever to the left as that graph keeps extending down and to the left. So our domain is going to be all real numbers, so -infinity to infinity. And for our range, we can see the same thing for the y values. It looks like a lot of the graph is contained between like -2 and 1, but you can see it going up forever and down forever. So we can cover every possible value on that y-axis, or that vertical number line as well. All right, for continuous functions and domain restrictions, we'll do a little bit of looking at the graphs and a little bit of computation to figure out some values, at least with functions we're familiar with so far. So note here, we'll see a formal definition in calculus, but for now we'll just use the definition below for a continuous function. So definition, a function is continuous if its graph has no breaks or jumps. And we often say if you're able to draw the graph without lifting your pencil. So for 2 here, we want to determine whether the graphs represent continuous functions and then find their domain and range. For the first graph, we can see if we were drawing it, and there's a piece that extends out to the left and comes down along the y-axis, and then a piece that's coming from the top along the y-axis, and then extending out to the right along the x-axis. There's definitely 2 pieces there, so we do not have a continuous function. I'll often use CONT for continuous, DISC for discontinuous, but not continuous. We can see there's very clearly a break in this graph. We could even say, if I can write a B, break at x equals 0. For our domain and our range, we can see along the x-axis, we come in, but never actually touch that y-axis, and then keep going out to the right forever. So we can go with a -infinity to 0 union 0 to infinity. And sometimes these ones where you're just cutting out a value are easier in set notation. A lot of the time you'll be asked for interval, so I'll probably stick to that for most of it, but we could say x such that x is not 0. And for the range here, we can see the same thing happening. We do not ever hit that x-axis, but it runs down forever along the y and up forever along the y-axis. So we've got a -infinity to 0 union 0 to infinity. Or to see the set builder for the range, same thing but with a y. Y such that y is not 0. All right, for B, I might recognize that square root function. A was the 1 over x, our reciprocal function, so we see some of those toolkit functions coming in. We'll add some work to our cards in class. But B, we can see, is continuous. Right, it starts at 0, 0, and then extends out and up to the right forever. So there's no breaks or jumps or anything in the graph on its domain. Our domain for that square root function, we start at 0 there and move out to the right. The fact that we have the point at 0, 0 means we're including it, so we've got that bracket, 0 to infinity. For our range, very similar. We're starting there at 0, 0, and the graph is extending up forever, out to the right. So we're going to hit all those y values up that axis as we go. So we can say our range is also bracket 0 to infinity. For C, we've got a graph that's in a few pieces. Hopefully we can see that. So not continuous, or we can say discontinuous, but continuous or not, we'll say not continuous here, and we can see that break in the graph at x equals 1. For our domain and our range, we can see the function extends out or comes in from the top left and then extends out forever down and to the right. So as we move along that x-axis, we've got everything out to the left. We come into 1 and we do see those two holes, but we also have a function value defined when x is 1. So 1 is included, and then that linear piece continues off to the right forever. So our domain here is all real numbers, so minus infinity to infinity. Any x we sub in, or any x I asked you about, you could find me a y value or a function value that corresponds to it. For the range, looks different, but very similar. This piece to the right that's going, or the linear piece, to the right that's going down and right forever, is going to go slowly. We can't really see it going off the graph. It looks like there's a bottom here at -4, but with that piece moving down and right forever, it's going to cover the whole bottom of the number line. And the piece moving left and up forever is going to cover the whole top of the number line. So our range here is also all real numbers. Every y value is going to be represented by some x. So graphically, hopefully we can see domain and range. If not, we'll practice more together. But if we want to work with equations, we have some ways to find our domain restrictions. So our note here, to find domain restrictions for a function with a denominator, a rational function, we find values where the expression in the denominator is equal to 0. Right, you may have heard before, we can't divide by 0. For square root functions, we can set the expression, called the radicand, under the radical greater than or equal to 0 to find its domain. We can't have those negative values under any even index radical, so square roots, fourth roots, sixth roots, but generally we'll talk about square roots. And we'll talk about what happens when we do have a negative under there later on. And so logarithmic is the other one you may have seen before. It's our other big restriction. We can set the expression, the argument inside the log, strictly greater than 0. So if you remember the toolkit function, that's the one that starts down along the y-axis, comes up through 1, 0, and then moves off to the right forever. So for 3, we want to find the domain for the given functions. And we have one recall here that's really for the second two. But when we are multiplying or dividing by a negative value, we need to remember to change the direction of any inequality symbol. So we'll do that when it comes up. But for f of x, for a, f of x equals 1 over x plus 3, we want to start by finding our domain restrictions, because we're working with a rational function, right? A fraction there. And we can't have that denominator equal to 0, so we can say x plus 3 cannot be 0. And we can do our work to find what value for x makes that happen. If we subtract 3 from both sides, we find that x cannot be -3. So we've got some room here. I wanted to practice writing that set notation a little bit for you in case it comes up or you're allowed to use it some places. But we'd go from -infinity to -3. That's the one we've got to cut out, the only thing x can't be. And then union up from -3 off to infinity. For our set notation, so that's our domain, our set notation would be x such that x is not -3. So again, a little bit easier to write that one when we're just cutting out a point, but you want to be familiar with the interval notation as well. You'll see it a lot more often. For b, f of x is the square root of expression minus 2x plus 3 under there. So we want to take that radicand out and say we need this minus 2x plus 3 to be greater than or equal to 0. So we can subtract our 3 from both sides. We get our minus 2x greater than or equal to -3, and then divide by that -2. When we do that, it changes the direction of that inequality. Ask if you have questions about why, but we have x less than or equal to 3/2 now, which we can put in our interval or set builder notation. So for our domain, this less than or equal to 3/2, we're going to the left on the number line. Those are all the numbers smaller, so down to -infinity, up to 3/2. That equality lets us use the bracket here. We can equal 3/2. That would just make a 0 underneath the square root, and the square root of 0 is still 0. For our set builder notation, we'd have x such that x is less than or equal to 3/2. For the log in C, we've got log of 5x minus 4. We'll talk about logs a lot more later. We're not really worried about the base or any of the points now. We just want to talk about the domain. So we need that argument inside, the 5x minus 4, to be strictly greater than 0. To solve for x, we can add the 4 to both sides. That gives us a 5x is greater than 4. And dividing by 5 won't change the direction, right? Just those negatives. So we find that x has to be greater than 4/5. For our domain then, we can say parenthesis, right? Not included this time, off to infinity. And our set builder notation, we just rewrite x such that x is greater than 4/5. All right, something that's probably new for most of you, we're determining limits and discontinuities from the graph. So note here in calculus, we'll talk about the limit of a function. To stick with less formal definitions, we can say a function has a limit at a point if as we zoom in around an x value, we also zoom in on a single y value, or function value, i.e. we approach the same height as we get close to an x value from the left and right. So we're not going to write a bunch of extra notation for left and right, but we will talk about it and try and draw a little bit, and hopefully look at it together in person, because it's a lot easier to kind of visualize this. But think if your hands are coming in from the left and right, kind of pinching in around an x value, we should only see one y value in that gap. And that's the kind of idea, we're just zooming in around a point. So really we're still just reading a graph and picking out a function value, but to have a limit, we don't actually need a value to be there. That's the difference. So note here, we use the notation limit as x approaches a of f of x to find the limit of a function f when x equals a. So we'll practice on the graph and we can try some more in person. But for 4, we're going to find the following values if they exist, and we'll talk about what to write when they don't exist. So for our limit as x approaches -1 for f of x, I'll try and scribble and then maybe erase. We can think as we're coming in from the left and from the right to pinch in around -1, and we just want to see what y value we're close to in there. So we can see both sides are coming to about the same point, -1, -1. So our limit here is going to be -1. We can see hopefully clearly from the graph that the function value there, f of -1, right? So when x is -1, our y value is also -1. For b, we're looking at the limit of f of x, this function, as x approaches 0. So as I come in towards 0 from the left and from the right, I get this window around 0. And depending on how far you draw in or pinch in, you can see there's no value even on the left, or really it's going down towards -infinity, right? As we come in from the left, this one's going down towards -infinity. As we pinch in from the right, this one's going up towards +infinity. So there isn't a single y value that we can see in there, right? We're going off in both directions. For that one, we put a DNE here, and we say the limit does not exist. You can also see, hopefully, there's no function value there, right? There's no point defined when x is 0. So we'd say that f of 0 is undefined, which just means it's not in the domain of f, right? There's no y value defined when x is 0. For c, we've got this limit as x approaches 1 for our function f of x. So we're going to pinch in around x equals 1. We want to think coming in from both directions. If we make a little window around 1, we can see a single y value in there at a height of 1. So our limit here would be 1. Our function value when x is 1, y is 1. For d, we're pinching in around 2, so our limit as x approaches 2 for f of x. As we come in along the function from the left and from the right, you can see we're getting really close to a height of maybe 1/2. There's no actual point there, but we still are getting close to the same height from both sides, right? You can see the function doesn't connect there because there's no point, but kind of connects to that hole. So we can see it's in the same spot coming from both sides. So our limit here is just, let's say, 1/2. But for f of 2, since there's no point anywhere, right, where x is 2, we can say, same as we did for 0, f of 2 is undefined. For our limit as x approaches 4 for this function f of x, as we come in from the left and from the right, we can see when we get really close from the left, we're down here around 1/4 or something. But as we get really close from the right, we're up here around 4. So we don't approach a single value. We're coming in towards two different heights from our different directions. So our limit as we approach 4 does not exist. But because that function value is filled in, is defined down here, when x equals 4, we say f of 4 is, I think I put 1/4, right? Something down there between 0 and 1/2. For the limit as f approaches 6, for letter f here, we're looking close to 6 from both sides, left and right. I don't know why I drew them at the point, it doesn't really matter, but we're zooming in around here. And we can see as we get really, really close from both sides, so maybe here as I move in along the function, I'm getting really, really close to this height of 6 from both sides. If I actually touch 6, I'm going to get that function value. We could put f of 6 here down at 4. But as I zoom in around 6, as I smush in from both sides, I can see my values approaching or getting really close to 6. So my value here is 6 for my limit, right? We can see that height that we're getting really close to from both sides. And we said f of 6 is 4. So the whole point of looking at that is to add a little bit more to, I guess, your vocabulary and kind of what you can say about a function. The discontinuities are hopefully a little bit easier to pick out, and then we can kind of relate the two using the limits. So if we want to identify values for 5 here where the function has discontinuities, hopefully we can see 0, there's definitely a break. And we can say the function goes off towards infinity. Or you can say the infinities, because really it's both, right? One from the left, we go down towards negative infinity. From the right, we go off towards positive infinity. Another place we have a discontinuity. We can see when x equals 2, we've got a hole there, very simple, right? So we'd have to pick up our pencil, continue on the other side of 2. For the next one, we've got a problem at 4. We can see a hole there, but also a jump or a big break in the graph. And the last one, just to scroll up for a sec, we can see it again at 6. We've got that hole with the function value defined somewhere else, but we'd have to pick up our pencil to draw that new point at 6,4. So here at x equals 6, we have a hole, and we can say the function is defined elsewhere. Your big takeaway from this is just where we do have breaks in the graph. And we'll add a little extra info below here for types of discontinuities, which we can pull from kind of what we wrote in words for 5 there. So note we can categorize these discontinuities into one of 3 types. We have infinite discontinuities. Hopefully, as the name implies, that's what happened at around x equals 0, where the function goes off towards the infinities. You can also throw in the words here. Some of you may have seen them before, but we haven't done a lot of the graphing yet. We have vertical asymptotes. So that's what you'll see at those infinite discontinuities, the graph running up or down along some value. We also have jump discontinuities. And here we can see the graph actually jump from one point to another. All right, so here we can say function or graph jumps from one piece to another. And we saw that around 4. right? Two completely separate pieces of the function. And then we have the last one, which are called removable discontinuities. And this is where pieces of the graph are just separated by a hole. So still both sides kind of connect to the same spot. So you can see the difference hopefully between what's happening at 2 and 6 versus what's happening at 4. Right? So for both of these, both sides of the graph we're still coming to the same spot. So really, if we want to down there, we can say the limit exists. Right? Our limit as x approaches a of f of x exists, but our function value f of a is undefined, like we saw around 2, or a different value, like we saw around 6. Right, so undefined here was at x equals 2 above, and a different value was where x was 6 above. So we want to watch out for those big jumps, those running up and down along or towards the infinities, and then places where we just have a hole, right? So here, connected around a hole. Write whatever makes sense for you there. But we can see the function still comes to the same spot. That's why we brought in these limits, right? The limit exists, we approach the same height, but there is a hole in the graph there. And we'll talk about it more when you get to calc, why it's removable versus non-removable or infinite or jump, but that's it for our first set of characteristics. So try the ticket.